So now that we've talked about solubility rules, what exactly does it mean to be soluble? Soluble will mean basically means it dissolves in, and usually the solvent is water, so we mean water. So how can we describe soluble? Well, I know if I add a little bit of salt to water, it'll dissolve because it's soluble. Sodium chloride, alkali metals are always soluble. However, if I keep adding solute, there won't be enough water molecules to surround the ions in a process called solvation, and they'll begin to settle out. So there's not enough water molecules to surround all the solute particles, all the salt, and they'll start to settle, just like in this picture. So, what are some descriptions of solutions and whether or not they've reached a maximum or a solubility limit of ions dissolved? So there's a couple terms. Saturated solutions. The term saturated means it's maxed out, it's saturated. You cannot dissolve any more solute. It's been maxed out for that particular temperature. If you put any more solute in, it will precipitate out or settle out. It's not really forming a precipitate, there's no reaction, but there's no more water to surround the salt and it settles to the bottom. Unsaturated solutions means they're not maxed out. There's enough solvent water molecules to surround the solute, and you can still dissolve more. So an unsaturated solution means you can dissolve more in it. Saturated means you've reached the max. You can't dissolve, it's maxed out. A supersaturated solution is when you trick a solution in dissolving more solute than it actually can for that temperature. These are unstable solutions. Typically, the way this is performed is you can heat a solution up, dissolve more solute, and then slowly cool the solution without disturbing it. If you've ever made rock candy where you dissolve a bunch of sugar in water and let it slowly cool, that's an example of a supersaturated solution. And then you might put a popsicle stick with a string so that the sugar crystals grow on the string and makes the rock candy. That's an example of how you can disturb the supersaturated solution. And now all of the solute that's dissolved will start coming out. So what does that look like? So here's an example of a supersaturated solution. On letter A, we've dissolved more than this solution can actually hold. How do we do that? We heated it up and slowly cooled it down. Once we cause a disturbance, again, a disturbance might be as simple as taking a glass stirring rod and scratching the side of this beaker. Or it might be adding what's called a seed crystal into this supersaturated solution. Once there's a disturbance, now it realizes, oh, wait, there's way too much solute dissolved in here, and all the excess for that temperature will come out and settle out of solution. So, what does it mean to soluble or solubility? Again, solubility is the maximum amount of solute that dissolves in a specific amount of solvent. Now, obviously, if I add more solvent, I can dissolve more solute. It's proportional. So how do we measure solubility? Typically, it's expressed in the grams of solute per 100 grams of solvent. And again, usually the solvent is water. It's the universal solvent because not only is it abundant, but because it's so polar, it dissolves polar compounds and ionic, because ionic is just an extreme case of polarity. Like dissolves like. Polar things will dissolve in polar water. So we can use this as a ratio and we can determine things, grams of solute per 100 grams of water. So here we see a solubility table. And on the table, just as we expressed earlier, this shows the solubility of grams of solute per 100 grams of water. And then down here, we see the effect of temperature. So typically what happens is Solubility depends on temperature. Why? Well, solute, especially salts, are going to have to be surrounded by water molecules, right? Or they're going to have water molecules come in, collide, and pull the ions out of their lattice structure. So you need a pretty active water molecule that's going to be able to surround its solute. So with an increase in temperature, water is going to move faster, it's going to be more active, and it's going to interact with the solute better. So we see solids pretty much increase with temperature increases as far as their solubility. Now, there are some cases like sodium chloride where it kind of flatlines, but for the most part, it's consistent. Now, how do we read the solubility limit curve? Well, we can take a given temperature, let's say at 30 degrees Celsius, which is roughly right there. I want to know how much potassium nitrate dissolves per 100 grams of water. I would go up from 30 and I would see roughly 60 grams of potassium nitrate can dissolve per 100 grams of water at 30 degrees Celsius. Now, if I'm at 60 degrees Celsius and I want to know how many grams of sodium chloride, I go up from 60 and I see right there for the sodium chloride, 40 grams of sodium chloride will dissolve per 100 grams of water. Now, for gases, solubility actually decreases as temperature increases. And why is that? So, a lot of people don't realize that gases already have a ton of kinetic energy. They're moving around fast and they have very low solubilities to start with. Okay, you can't get a lot of gas to stay in water. If you start heating the solution up and giving the solution more kinetic energy, the gas is just going to fly out. So, opposite of solids. So, solids tend to have an increase in solubility when temperatures increases. Gases are the opposite. Their solubility decreases as temperature increases because now they're flying out of the solution. So what is a way that we can increase the solubility of a gas? That's what Henry law states. The solubility of a gas in a liquid is directly related to the pressure of the gas above the liquid. So soda pop, right? I was a weird kid. I used to buy a 2-liter bottle of Coke, and there'd be a space above it. And I'd get angry because I felt like Coke was ripping me off. But what I didn't realize is that space was required to keep the Coke carbon or to keep the Coke carbonated and have the CO2 in it. So that space above this soda can basically has a high pressure of CO2 molecules, right? So now the CO2 in the cola can't escape out because there's no room. There's the pressure of the CO2 above it. As soon as I open this can up, now it's open, it's not a closed system, and the CO2 can escape into the atmosphere. When the CO2 escapes, now above the cola, there's fewer CO2 molecules and there's less pressure pushing down on this liquid. Well, now there's less pushing down on the liquid. The gas in the liquid, the CO2 in the liquid, can fly out and escape. So Henry law states that the solubility of a gas in a liquid is related to its pressure above the liquid. At higher pressures, more gas molecules dissolve in the liquid. Whoops. At lower pressures, right, less gas will dissolve in the liquid. So if you leave a beer out, especially in warm weather, what happens? It gets flat. Why? Because the CO2 gas escapes. What happens when you pop the cork of champagne? All the CO2 rushes out because it doesn't have that closed system above it and that high pressure. So now the carbonation can escape. I hope that helps you understand solubility in terms of when is something saturated. unsaturated or supersaturated, and what the effects of both temperature on solids and liquids are, and what the effect of pressure is on gases.